Hello, can you hear me?
Yes, sir.
Okay. So let's start with today tutorial. In today's tutorial, I will be solving some problems related to boiling, and then I will start some questions from fundamentals of radiation heat transfer. So I will solve few two or three problems related to boiling heat transfer, and then some three or four questions related to spectral heat transfer due to radiation, and a few questions about emissivity, like spectral emissivity and total emissivity. So let's start with the today's tutorial. So this question, so in this PDF is the continuation from the previous tutorial. So I was included a few questions from boiling heat transfer in the previous PDF. So I will continue from that. So for today, the first question is explain the boiling curves. So in the heat transfer, we have a boiling curve which is uh, made in a heat flux and temperature plane. So my y-axis is heat flux and my x-axis is temperature difference. Let's say 5, 30 and 120, so on. So in the boiling, start with increasing the temperature difference. So just a minute. So my as my temperature increases, my heat flux increases, and therefore there is a linear variation uh, in the heat flux from 0 to, let's say, point A. So in this regime, the boiling is due to the free convection heat transfer. So as we increase the temperature from 0, there will be a free convection, which is in laminar flow, and on increasing the further temperature, that laminar free convection turn into a turbulent free convection, and hence there will be a increment in the heat transfer coefficient also, and that heat transfer coefficient is the natural heat transfer coefficient. And to find out the that heat transfer coefficient, we already solved few problems in the last week based on the correlation we used. So here there is a increment in the heat transfer also. So first there is a laminar based heat transfer coefficient which turns into turbulent based heat transfer coefficient. Since in a turbulent flow there is a more mixing within the fluid, and therefore it will be fluid can able to transfer more heat, and therefore it result into a more higher heat transfer coefficient. So till point, let's say 0 O to A, the boiling the law which governs the boiling heat transfer is from the free convection, both laminar and turbulent based uh, empirical models. After point A, the nucleate boiling start happens, which means that the surface temperature is more than my saturation temperature, and here there is a sharp increment in the heat flux as well as the my heat transfer coefficient. So let's say this is my point B. So here what happens that uh, lot of bubbles start appearing into the systems, and these bubbles actually translate to the upper side. And due to these bubbles, there will be a lot of mixing between the bubbles and the surrounding fluid, and the flow become very turbulent in nature. And this turbulence increases with increasing the number of bubbles, and also when the bubbles started rising into the columns, so which severely increase the heat transfer coefficient as well as the heat flux. So from point A to B, there will be a sharp increment in the heat transfer coefficient. And after point B, what happens? It increases the heat flux as we increase the temperature, but the heat transfer coefficient start decreasing. So let's say this is my point P. So here my heat flux is increases, which is obvious from the plot, but my heat transfer coefficient start decreasing, and this happens due to a lot of bubbles that are created into the systems. And now since bubbles are the void of airs, the heat transfer coefficient of air is less than heat transfer coefficient of fluid, surrounding fluid. Then at some point of time, it will reach a maximum heat flux. And here, my heat transfer coefficient at, let's say this is my point C, my heat transfer coefficient here is less than my heat transfer coefficient at D and even at P. Now at point C, there are a lot of bubbles which are created, start merging, which creates a slug kind of a flow. Now when this happens, it start covering the surface of the heater. So when this happens, my heat transfer coefficient will start decreases, and on further increment in the temperature, it suddenly become decreases to a minimum heat flux here, which is, let's say, point D. So this is my transition regime. This is my nucleate regime. So in the transition regime, what happens that those large slugs which made due to a combination of various kinds of bubble, it appears at the top of the heater, and there will be no convection heat transfer. There will be no proper convection heat transfer from the surface of the heater to the fluid, and the heat transfer mostly occurs due to the conduction. There will be a conduction heat transfer through the air. So let's say this is my heater, and this is my surrounding fluid, and there will be some layer of slug which contain only air appear at the top of the surface heater, and the heat transfer through this slug occurs due to conduction. And we know that the conduction property and the heat transfer coefficient of air is very, very small, and therefore as we increase the temperature, the heat transfer coefficient and heat flux will fall down, and it will fall down to the minimum heat flux value. Now when we keep increases the temperature from here, from point D, this heater will get too hot, and it start radiation. It start emitting radiation, and therefore there will be a radiation heat transfer. So the further heat flux or the further heat transfer also contained due to radiation, and therefore there will be again increment in the heat flux, and this increment in the heat flux occurs due to the radiation heat transfer. So in the transition regime, we can go to directly to this D, let's say this is my E at infinity, somewhere here. We can easily go to at DE region, which is film boiling region. So from CD, we can either translate to fill boiling region or to the nucleate boiling region. And this is a very short region in time, which means that sometimes if depending upon the various parameter like various heating controlling parameter, you can easily go to this region. And only we step by step control the heating parameter in time, we can obtain this transition region here. So this is the rough sketch of the boiling curve, or just a revision for the boiling curve. It helps us to understand or solving the various problems related to the boiling region. So any question in this? Not, then let's move to the next question. So in this question, we have a bottom of a copper pan, 0.3 meter in diameter, is maintained at 118 degrees Celsius by electric heater. Estimate the power required to boil water in this pan. What is the evaporation rate? Estimate the critical heat flux. So we need to find the total heat transfer as well as the critical heat flux, which is basically a maximum heat flux, because after that there will be a either film boiling which started occur, or there will be a shutdown in the system, because the electric resistor, depending upon the properties of the material used in the electric heater, either it went off or it will continue to the film boiling region. So basically critical heat flux is the maximum heat flux we need to find, and the total heat required to boil this water in this pan. So for this we will be using some correlation which is given for the nucleate heat transfer as well as for the maximum and minimum heat flux. So let me write down the properties of fluid. So my density of the liquid is 979.9 kg per meter cube. Specific heat of liquid is 4217 joule per kg Kelvin, and my viscosity of fluid is 279 10 to the power minus 6 Newton second per meter square. My Prandtl number of fluid is 1.76. My latent heat is 2257 kilojoule per kg. Surface tension is 58.9 10 to the power minus 3 Newton per meter. And my density of vapor is 0.595 kg per meter cube. So these are my some properties here. And my excess temperature is temperature of surface and saturation temperature. So the temperature of surface is given in the question is 118, and my surface temperature is, saturation temperature is 100 degrees Celsius. So my excess temperature will be 18 degrees Celsius. So to determine the heat transfer, in nucleate boiling region, I will use the correlation. So here CSF and N are just constant based on the properties of material and the fluid. So we have all these values, and the constant value of constant for the copper surface is given here. So we just need to plug the values. This is my dynamic viscosity. My latent heat transfer coefficient is 2257 in kilojoule per kg. My liquid density is 957.9 and my vapor density is 0.595. And my surface tension coefficient is 58.9, 10 to the power minus 3. Multiply by my latent heat. My excess temperature is 18 degrees Celsius. The constant is 0.0128. And the Prandtl number is 1.76. So on calculating this, we will get the heat flux as 836 kilowatt per meter square. So to find the total heat, I have to multiply this heat flux with cross-section area of the heater. So this is my cross-section area, and we have given a diameter of 0.3 meter. So my total heat is 59.1 kilowatt. So this will be my total heat. So now we need to find what is the evaporation rate. So by using the energy balance, we know that whatever the heat we are adding here, whatever the heat addition to the pan will result into the evaporation. So whatever the heat we are adding to the fluid, it will evaporate the fluid. So basically I can write as heat required to evaporate is mass multiplied by my latent heat. So we need to find the evaporation rate, which means we need to find the mass here, the total mass flow rate of evaporation. And we already found the total heat transfer required for the boiling, and that total heat will evaporate the remaining liquid at the top. So my heat transfer, which we found, is 59.1 kilowatt. And my latent heat was 2257. Which means my mass flow rate will be 0.0262 kg per second. So this will be my mass flow rate. Now I need to find the critical heat flux or the maximum heat flux. So basically we are finding the heat flux at point D here. Until now we just find the total heat flux in the nucleate region, and then we found the total heat transfer by multiplying it with area. Now our objective is to find the heat flux at point D. Heat flux at point C, which is the maximum heat flux or the critical heat flux, not D. So we are finding the total heat flux at point C here. So for this, we will use the correlation. We already have a correlation for maximum heat transfer, which is given as so we just need to plug values in the above correlation. So this is my latent heat. My vapor pressure is 957 multiplied by surface tension coefficient is 58.9. So we just need to calculate the above quantity here. So my maximum heat transfer after calculating this will be about 1.26 megawatt per meter square. So in this question, we have given a diameter of the heater, and it is said that the heater is maintained at temperature 118 degrees Celsius, and we need to find the total heat transfer, the maximum heat transfer, which is critical heat flux, and the evaporation rate, which is mass flow rate, amount of the mass flow rate the liquid gets evaporated due to heating. So for the total heat transfer, we use the correlation for the nucleate boiling. So this is my heat flux for the nucleate boiling. We found first the heat flux using this correlation, and then we multiply it with area to find the total heat transfer in the nucleate boiling region. Then to find the total mass flow rate, evaporative mass flow rate, we use the energy balance, where we say that whatever we input the heat, whatever there is heat due to heat input due to the electric heater, that heat will be convert the vapor liquid into the vapor, and therefore this heat transfer will be equal to the heat transfer, latent heat transfer multiplied by the rate of evaporation. So we found the rate of evaporation just 0.0262. So we already given the latent heat transfer, and we already found the total heat transfer in the nucleate boiling region. Then to find the maximum heat flux, we again use the correlation here. We just put the values, whatever the values we have given here in the correlation to find the maximum heat transfer. So any doubt in this question?
So the relations you are using for maximum and for the surface heat transfer, is there any name for these relations?
Remember, there is no name of it, but it can be found in the textbook, or whenever they ask in the exam, they should given this relation in the question itself. So you don't need to remember this by heart.
Okay.
So here from again just to revise from O to A, we need to use the correlation that we discussed in the last tutorial, which is based on the free convection, and we need to use the Nusselt number based on laminar free convection, turbulent free convection. For A to C, this is my point C. So for A to C here, we need to use this relation here for calculating the heat flux, and we can easily calculate the total heat transfer when we multiply this by area. And then we have a separate correlation for maximum heat transfer, which is at point C, and minimum heat transfer also, which is at point D. Then we have some correlation based on Nusselt number and heat flux, heat transfer coefficient in the film boiling region also, in this region also. So let's move to the next question. So in this question, we will be discussing correlation based on the film region on the boiling. So in this question, a metal clad heating of 6 mm diameter and emissivity is 1 is horizontally immersed in water bath. The surface temperature is 2 to 5 degrees Celsius under steady state boiling condition. Estimate the power dissipation per unit length of the heater. So let me write down the properties again here. So density of fluid is 957.9 kg per meter cube. My latent heat is 2257 kilojoule per kg. My density of vapor is 0.459 kg per meter cube. Specific heat of vapor is 1.98 kilojoule per kg Kelvin. Thermal conductivity of vapor will be 0.0299 watt per meter Kelvin. My dynamic viscosity of vapor will be 15.25 10 to the power minus 6 Newton second per meter square. So this is for fluid and this is for vapor. Now I have given a metal clad here, which is a heating element, and there is a surrounding water. And as we increase as the metal clad is heating, there will be boiling occur in the surrounding fluid, and we need to find the power dissipation per unit length under steady state boiling condition. So we have given the surface temperature of the metal, which is 255 degrees Celsius, and from the plot we can see that this is corresponding at film boiling. The surface temperature is actually falls far from the nucleic regime, and it is actually at film boiling regime. So we will be using the correlation based on this film boiling heat transfer here. So here my excess temperature will be, this is the given temperature and the surface of heater, and this is my saturation temperature. So this is my surface temperature and this is my saturation temperature, and my excess temperature will be 155 degrees Celsius. So it will lie somewhere here. So the boiling is at the film boiling region. That means the region between D and point E. So here the heat transfer will be governed by Newton's law. And this is my surface temperature difference. So as I discussed that in the film boiling region, there will be an increment in the heat flux, and that is also due to the radiation heat transfer. So there will be convection heat transfer, and also there will be a radiation heat transfer. So my heat transfer coefficient is based on convection heat transfer plus radiation heat transfer. So in the earlier week, I may have solved some problem like in week 1 or week 2, where I showed that apart from using the Stephen-Boltzmann law, we can also combine our convection and radiation problem together. So in that case, we have to form the heat transfer coefficient based on the radiation. So here for the film boiling, my relation for the heat transfer coefficient will be given as so this is my relation to find the heat transfer coefficient in film boiling. For the general case, for the cases I may have solved problem in week 1 where there is a convection and radiation heat transfer, and we wish to find the heat transfer coefficient based on the radiation, we can use this relation. For the film boiling, we have to use this relation here. So here my heat transfer coefficient is a function of convection heat transfer as well as the radiation heat transfer. So for convection heat transfer, I can again use correlation which is appropriate for the film boiling. This is my thermal conductivity and my vapor pressure is ρV. This is my fluid density. Sorry, this is my vapor density. This is my fluid density. So this is a correlation for heat transfer coefficient for convection process. So we just need to put the values here. My thermal conductivity of vapor was 0.0299. My density of vapor was around 0.49, and density of liquid was 957.9. And my latent heat is 2257 kilojoule per kg. My heat capacity for vapor is 1.98 in kilojoule per kg, and my excess temperature was 155. The dynamic viscosity of vapor is 15.25. And the diameter is given as 6 mm. So we just need to calculate this, and on calculation I will get my heat transfer coefficient for convection or due to convection as 238 watt per meter square Kelvin. So this is due to convection. But there is an increment in the heat flux due to radiation also. And we saw that for the film boiling, my heat transfer coefficient is also a function of radiation heat transfer coefficient. And to find the radiation heat transfer coefficient, I will be using formula. So here I'm using the energy balance. For example, my heat transfer due to radiation is equal to, let's say, Stephen Boltzmann law. So this is my heat transfer due to radiation, normal heat transfer due to radiation, and this is due to radiation inside the liquid, inside the fluid. Because we have a heater here, and there, which is surrounding in the fluid, and there is a radiation heat transfer from the heater. So in that case, there will be a heat transfer coefficient due to radiation, which is equal to the actual radiation heat transfer, which comes due to Stephen Boltzmann law. So my heat transfer coefficient due to radiation becomes this. So we need to use this relation to find the heat transfer coefficient due to radiation here. So emissivity is 1 and Stephen Boltzmann constant is 5.67 10 to the power 8 watt per meter square Kelvin, and the surface temperature so here to find the heat transfer coefficient from radiation, we need to use the temperature in the Kelvin here. So I will be writing the temperature in Kelvin. So this is my surface temperature in the Kelvin, and this is the saturation temperature in Kelvin. So on calculating this, heat transfer coefficient due to radiation will be 21.3 watt per meter square Kelvin. Now I have to use the equation 1 here. So the equation one is not possible to calculate analytically. That means from using standard rules of mathematics, we cannot calculate because there is an unknown quantity here, h, at the right hand side, and again unknown quantity at the left hand side. So then we have to use the trial and error method. Sorry, 1 by 3. We already know this and this, so we put here the values. My convection heat transfer coefficient is 238, 4 by 3. My radiation is 21.3. Now we can use trial and error method. We can multiply both sides with h cube. So it will vanish h here, but the h cube will again appear here, and there will be a h here also. So it doesn't make much difference. So we need to guess the value of h here. So by using the trial and error, we will be getting hs. Let's say my approx value of h will be 254 watt meter square Kelvin. So when I substitute h here, I can use so this is my guess value, which should be at least above from 238 plus 21.3. So based on it, I mean, from the solution, people have guessed this value. So let's say this is my total heat transfer coefficient, and then we put this total heat transfer coefficient in equation, let's say A, to find the total heat flux, which is approximately equal to 254 by 6 10 to the power minus 3 multiplied by 155. So my heat transfer, approximated heat transfer will be around 742 watt per meter. So in this question, again, we have given a diameter and the surface temperature. And to use the correlation, that which correlation we need to use to find the heat flux or heat transfer coefficient, we need to check the excess temperature, this excess temperature. And from the plot, heat boiling plot, we can identify the region at which are the region we are talking about here. So based on the excess temperature, we know that we are talking about film boiling region, and hence we need to use the coefficient correlation for the film boiling. So we used we use this equation one as a correlation for finding the heat transfer coefficient in the film boiling region, and there is a contribution due to convection and radiation part. For convection part, this is a correlation in film boiling. And to calculate the radiation heat transfer coefficient, we just use the energy balance. However, since the equation 1 is self a very complicated equation, so we need to use the trial and error method. So one way to approximate the total heat transfer is your total heat transfer should be more than your convection plus radiation heat transfer. So based on this, at least we can say that it should be more than this, and we guess the value of total heat transfer, let's say 254, and based on this we approximately calculated the heat flux in the film boiling region. So any doubt in this question?
No, sir.
So let's then move to the radiation part, radiation heat transfer. So in the first question, consider a small surface of area A1, 10 to the power minus 4 meters square, which emits diffusely with a total hemispherical emissive power of 510 to the power 4 watt per meter square. And we need to find at what rate is this emission intercepted by small surface area A2, which is oriented as shown, and what is the irradiation G2 on A2. So we have given here area of 10 to the power minus 4 meters square with the emissive power of 5 10 to the power 4 watt per meter square. And we need to find the heat rate at which emission from A is intercepted by A2, which means that there will be a heat transfer due to radiation from surface 1 to 2, which is my total spectral hemispherical emissivity or the intensity due to surface 1 multiplied by area, and this is my solid angle d omega. So I need to calculate the intensity, diffusive intensity, and the solid angle here. So my diffusive intensity will be this. We already have given this emissive power, diffusive emissive power, which is 5 10 to the power 4. Okay, let me just put in the equation 1 itself. To calculate the solid angle, you can just approximate this as A2 so this is my solid angle here. Now my heat transfer from surface 1 to 2 will be this. total diffusive power is 510 to the power 4 8 pi, and my surface area at 1 will be 10 to the power minus 4, and at 2 it is 510 to the power minus 4 meters square. This is my theta 2. This is my theta 1. My theta 1 is 60 degrees and my theta 2 is 30 degrees. And my R2 is the distance between my plate 1 to plate 2. So my R2 is 0.5. So my heat transfer from 1 to 2 will be 1.37 10 to the power minus 3 watt. Now to calculate the irradiation, at surface 2, so irradiation basic is the amount of this radiation which is received by surface 2. So whatever the radiation emitted by the surface 1, it will be received by surface 2. So the total heat transfer from surface 1 to 2 will be 1.37, and my irradiation will be the total heat transfer from surface 1 to 2 divided by cross section area. So it will be around 2.76 watt per meter square. So this is my irradiation at surface 2, and this is my heat transfer from surface 1 to surface 2. So any doubt in this?
So you are writing here only A. Why you are not writing A1 or A2?
Where? Oh, sorry. Here it is A2. This is because we are calculating a surface 2, whatever the radiation received to surface 2 from surface 1. So irradiation at surface 2 will have the area of surface 2, because this is the irradiation at surface 2. So whatever the surface 1 will emit, it will receive by surface 2. So this total receive is actually a irradiation divided by A2.
So then how is it different from the view factor?
So as of now, for this is a very simplified case. So here is no difference between the radiation emitted by surface 1 and captured by the surface 2. But let's say my surfaces, there are my multiple surfaces which is arranged around the surface 1. In that case, it depends upon the directionality of the radiation, and based on the directionality, my view factor will decide it, and depend upon the view factor, the surface at which the heat radiation is receiving will be different. So here my view factor is 1. That means whatever there is emission from surface 1, all the emission will be captured by surface 2. But based on the orientation, let's say my surface 1 is here and there is different orientation. This is my different orientation, and it emit the radiation in all direction, let's say. So this emission is actually Q1, and N is different surfaces. Now the way this N1, N2, N3 and N4, these surfaces receive the heat depend upon the view factor. And since the orientation and the location of this surface are different, my view factor of each surface like N1, N2, N3 will be different. So let's say my view factor here is F1, here is F2, F3. So here F1 not equal to, every view factor will be different. And then my heat transfer received will depend upon this view factor multiplied by this heat transfer from 1 to n. So since my view factor is different, my heat transfer received by each surface will be different. But for this case, my view factor is 1. So basically whatever the radiation is emit, it is actually received by the other surface.
But it is not indicated anywhere from the statement of the question.
So it is said that there is a diffusive heat transfer, which means that A1 will emit in every direction, and therefore it doesn't matter what is the orientation of A2. It will capture all the heat, whatever A1 is emitted here. It is like you have a surface here and one surface here also. So whatever there is a emission from surface 1, it will go to the whole emission will capture by surface 2.
Diffusely means that intensity of radiation will be same in all directions.
Yes.
It doesn't indicate that all the radiations will be captured by A2, because diffusely means radiation intensity will be same in every direction.
Yes. So my density of radiation here will be same as here, and here. So it will capture the same amount of density. Doesn't matter if I place A2 here, my view factor is still 1. It will capture the same amount of density. If you place A2 here, again, since my view factor is 1, because the same amount of radiation density will be captured by surface A2 here also. So everywhere my shape factor will be 1. It will only change the intensity of the heat transfer because it depends on this angle. Otherwise, whatever the intensity I will get, the whole intensity it will capture. The other surface will be captured because of this diffusive nature of surface 1. Because my density of radiation is everywhere same. So it doesn't matter where I place my surface A2. It will capture all the radiation from surface 1. Only the difference is the heat transfer from surface 1 will be changing. That is different thing.
Okay, sir.
Yep. So let's move to the next question then. So according to its directional distribution, the solar radiation incident on Earth's surface may be divided into two components. The direct component consists of a parallel ray incident at a fixed angle theta, while the diffusive component consists of a radiation that may be approximated as being diffusely distributed with theta. Consider clear sky for which direct radiation is incident at theta 30 degree with a total flux based on an area that is normal to the rays. Of Q, the flux is given as 1000 watt per meter square, and the total intensity of the diffuse radiation is 70 watt per meter square. Dot SAR, what is the total solar irradiation and the Earth's surface? So in the question we have given that we have the incident, solar radiation incident on the Earth surface is divided into two components. So component due to the solar radiation, there will be a component due to the solar radiation, and there will be a contribution due to the diffusive radiation. So my irradiation will be due to the solar radiation, which is coming from a certain angle, and due to the diffusive nature of the radiation. And from solar radiation, I have given the heat flux. So my irradiation from solar is heat flux, and it is coming at an angle theta, 30 degree. So it will be 30 degree.
Excuse me, sir. What is the source of this diffused radiation?
Source is actually not given. It is just in the question it is given that there is a two kinds of irradiation. One is from the sun, which is direct, and one is diffusive in nature. And we just given the total intensity or diffusive intensity. That's it.
So can you show the statement?
So here it is. So it just says that there is a solar radiation which has both direct and diffusive in nature. My heat flux or the intensity due to direct radiation is different, which is given as in the form of heat flux, which is 1000, and my intensity due to diffuse solar radiation is 70 watt per meter square SR. And we need to find the total radiation. So the source of both direct and diffuse is same, which is solar radiation. It's just the magnitude, I guess, is differ. Therefore, in the question they are divided into two parts. One is diffusive in nature and one is just direct. But the source is both same, solar radiation. And since we have a two nature, like direct and diffusive nature, the irradiation will be comprises, one is due to the direct nature and one is due to the diffusive nature. Now we have given the unit vector n, so we can just measure our angle from vector n, which is 30 degree. So my irradiation due to the direct nature will be heat flux multiplied by cos 30, and due to diffusivity I can write simply as pi multiplied by intensity, which is I diff. So my total irradiation will be plus pi multiply intensity due to diffusive nature. So my total irradiation will be 1000 cos theta plus pi 70, which is 866 plus nearly 2220. So my total radiation is 1086 watt per meter square. So any doubt here, like in this question? So in this question, the basic they just divided the nature of solar radiation into two components, direct and diffusive, and they asked to calculate the total radiation, so that whatever the sunlight received by the surface will be the radiation. Now, since the radiation is received by the surface are in two form, one is in direct form and one is in diffusive form. So the radiation will be again will be in two form. There will be a irradiation due to direct nature, and there will be a irradiation due to diffusive nature. So we just add both components here. So for the directionality, we have given the direction which is theta equals 30 degree. And for the diffusive nature, we use the total heat transfer, which is multiplied by total power, which is multiplied by pi into intensity here. And we get the total irradiation due to both components. So any query still on this? Any doubt? So let's move to the next question. So any doubt in the previous question?
So that emissive power you have used, that G is equal to pi into intensity. Can we use it for G direct also?
No. So this is valid only for the diffusive nature, not for the direct case. So for direct case, you need to use the integration and all. So then in the next question, I will use that. It will be more clearer from the next question.
Okay.
So the next question is, the spectral distribution of the radiation emitted by a diffuse surface may be approximated as follows. So So we have given a spectral distribution of radiation with different wavelength, and first we need to find the total emissive power, and then we need to find the what is the total intensity of the radiation emitted in the normal direction at an angle 30 degrees from the normal, and determine the fraction of the emissive power leaving the surface in the direction of pi by 4 to pi by 2. Okay. So let's start first one. So we have given a total, we have given a spectral emissive power, which is a function of this lambda, and my total emissive power will be using, so basically I am just doing integration over all the wavelength here to find the total emissive power, and we have given the emissive power corresponding to each and every wavelength here. So we just need to integrate here separately for this case, this case, this case, this and this case, and add all the emissive power based, which is a function of wavelength, to find the total one. So it can be written as 5 to 0. That means from wavelength 0 to 5, from 0 to 5 here, and my emissive power here from 0 to 5 is 0. Then from 5 to 10, and my emissive power from 5 to 10 is 100. Then from 15 to 10 in this region, and my emissive power here is 200. Then to 15 to 20, and my emissive power is 100 here. And from 20 to some infinity, it is 0. So this will be 0 again. So my total emissive power will be 100 multiplied by 10 minus 5. After I integrate this, 200, 15 minus 10. Hundred, 20 minus 15, and this is 0. So on calculating this, I will get 500, 2000. Basically it's 500 plus 1000 plus 500, which is 2000 watt per meter square. So this is my total emissive power. So for diffusive emitter, my intensity will be E by pi, which is 2000 by pi watt per meter square by SR. So we have given it is a diffusive surface here. So this is so in the part B here. So for the first part here, we calculate the total emissive power here. For the part B, we need to calculate the total intensity, which is for the diffuse emitter will be given by this. So it doesn't matter if it is at angle 30 or anywhere, because since it's a diffusive emitter, my intensity will be same everywhere. So it is independent of angle. Then we need to find the fraction of emissive power leaving the surface in the direction of from pi by 4 to pi by 2. For that, my fraction of emissive power from angle pi by 4 to pi by 2 is this. This is my total power, and this is my some specific some power in the specific range from theta pi by 4 to pi by 2. So my total intensity is just pi I, which is here for the diffusive nature, this one. And for some specific angle, the part of my total power for some specific angle is given as from pi by 2 to pi by 4, i.e. cos theta sin theta d theta d phi. So d phi will be always 0 to 2 pi, and based on the direction given in the question, the theta is from pi by 4 to pi by 2. So let me write just clear. This is my diffusive intensity. D theta d phi. So just plug the values here. I.e. cos theta sin theta d theta so for integration, this part will be just 2 pi, and this pi and pi, this will be cancelled here. And when I integrate this part, I will get sine square theta by 2 from pi by 2 to pi by 4 multiply by 2 and this will also cancel. So it will be 1 minus 0.707 square multiply by 2. So 1. So my 2 to cancel, and it will be 1 minus 0.707 square. So it will be so this is approximate equal to 0.5. So it will be 1 minus 0.5, which is 0.5. So this is my fraction of energy, which means that fraction of energy emitted between pi by 2 to pi by 4 divided by total energy. So this is my fraction based on the certain direction. So here in this question, we are given a spectral distribution of a diffusive surface, and first we need to find the total emissive power. So we just integrate it region by region to find the total emitted power. Then we ask to find the total intensity at some specific angle, but in the question it is given as the surface is diffusive in nature, which means that it is independent of direction, independent of theta, and we use the standard relation of diffusion, which is this, which means that my total power is just pi times intensity, diffusive intensity. And then we have asked to find the power in some specific range of in some specific direction, and we need to find the fraction of it power. That means we have to divide that power based on the specific range into the by total power. So for that we integrate it. So this is my power from pi by 4 to pi by 2, from theta pi by 4 to pi by 2, and this is my total power. So the fraction of this will be 0.5. That means half of the power is radiating from angle pi by 4 to pi by 2. That means if this is my surface, the half of the my total power is radiating in this region. So any doubt here? So if there is a, let's say, if we need to find the intensity which is not for diffusive surface, then we need to use this integration to find for the specific direction as well as for the specific wavelength. So any doubt?
So, sir, this should be independent of the angle. So, why we are calculating from pi by 2, pi by 4 to pi by 2? Because it is diffusive in nature.
Because this is the energy emitted from in a specific part from let's say pi by 4 here to pi by 2. So my intensity is independent of angle. That means my at every direction my intensity is similar, but my spectral distribution is, I think, which is leaving the surface, I think it is changing. Okay, let me get back to this. As of now, I have no clear explanation for this question. Let me give this proper explanation next week for this question. So again, one reason I could find it, my intensity for diffusive surface will be just my total emissive power by pi. Now I got this relation after this integration. That means if I, let's say, integrate in all the direction in theta and phi, I will, in the end, I will get this relation, which is E equal to I pi, and which means that my diffusive intensity will be E by pi. But my total power will be different in different direction, even though my intensity will be diffusive in nature. For example, here my total power is a function of wavelength. That means it is changing with wavelength. Similarly, my uh, total power should also change with the direction. So
but once it is diffusive in nature, it is independent of lambda also.
no, if there is a independent in lambda, then it will be spectral, right? Okay, let me again come back to this question next week, because I think something is there in the question. So okay, let me again solve this question next week. Is it fine?
Okay.
So for now, let's move to the next question. So this is multiple choice question, type of a question based on the boiling heat transfer. So we have given a typical boiling curve of water at 1 atmospheric pressure, and we need to find the correct options. So the first option is the region CD falls in the transition boiling regime. So is it a correct option?
Actually, your figure is not clear. It is not legible.
Is it, you know?
No, it is not visible to me.
Okay, let me draw the figure then. So the first statement is the region CD falls in the transition boiling region.
Yes, it is true.
Yeah, so the first option is correct. The second statement is the stirring and agitation caused by the entrainment of the liquid to the heater surface is primarily responsible for increase the heat transfer coefficient and heat flux in the region of nucleate boiling regime.
That is true.
Yeah, so basically there will be a increment in the heat transfer coefficient due to the mixing of different kinds of bubbles and the fluid, and these bubbles try to combine and try to form a slab, and during this process there will be an increment in the heat transfer due to this highly turbulent nature, as I explained at the beginning of this class. So this is also true. And the C statement is nucleate boiling is the most desirable regime in practice because high heat transfer rates can be achieved in this regime.
That is also true.
Yeah, so basically my highest heat transfer coefficient is lie between somewhere point B and C, and therefore to conduct a high heat transfer due to convection, this my nucleate boiling regime is favorable. So which means my option D is correct, which is all statement above are true. So let's move to the next question. So in this question, a dark surface of ceramic stove top may be approximated as black body. The burners which are integral with the stove top are heated from below by electric resistors heater. Consider a burner of diameter D 200 mm operating at a uniform surface temperature 250 degrees Celsius in an ambient air at 20 degrees Celsius. Without a pot or pan on the burner, what are the rate of heat loss by radiation and convection from the burner? And if the efficiencies of the burner is 90%, what is the electric power requirement? And at what wavelength is spectral emission of maximum? So first we need to determine the total heat transfer, which is combination, which is due to the radiation as well as convection from the burner. So we have given here a burner here, and the surface temperature is 250 degrees Celsius. And my ambient temperature is 28 degrees Celsius. Diameter is 0.2 meter. And there will be a radiation heat transfer plus convection heat transfer.
This dia is of the surface.
Yeah, it is this dia. So I think there is from the top side there it looks like a spherical surface of diameter 0.2 meter, and below this spherical surface there is a heater. So it is like this in some other view, and there is beneath this plate there is a heater placed, and there will be a radiation from this plate to top. So this arrow is actually pointing out from the screen, coming out from the screen. So there will be a heat convection in this direction, like that coming out from, which is coming out from the screen, from the surface of this plate, plus heat transfer due to the radiation. So which is exactly like perpendicular from the plate to this screen. This is from the top view or the screen view. So for the convection, let's find the convection heat transfer. So there is no velocity of a fluid, like there is no fluid which is flowing over the surface. So there will be no force heat convection. It will be a free convection. So for free convection, we need to first determine whether the flow near the pan is laminar or in turbulent nature. So from the last class, we know that to identify the nature of the flow, we need to find the Rayleigh number. So here alpha is the thermal diffusivity and nu is the kinematic diffusivity. We write the properties of air. So my kinematic viscosity, my thermal diffusivity is 39.7. volumetric coefficient is 0.00245 Kelvin inverse based on the temperature we have given, and my Prandtl number of air is 0.7. So based on this, I can find my Rayleigh number as so on solving this, my Rayleigh number will be 6.35 10 to the power 5. So for this problem, I will be using my Nusselt number correlation as Rayleigh 1/4 multiplied by 0.54
So it means you are using it for laminar?
Yeah, so that's 10 to the power 9,
Oh,
which
yeah.
is laminar.
Yes, yes.
And which means my heat transfer coefficient will be K by L 0.54 RA 1/4. So my thermal conductivity of the gas will be 0.0344 0.2, sorry, this is a T, and 6.35 10 to the power 5 1/4. So it will be approximately equal to 10.5. So this watt per meter square Kelvin. This is my heat transfer coefficient, and my heat transfer rate due to convection is given from Newton's law, which is 10.5 pi by 4 d square to much was that? 250 minus 20, and my heat transfer due to convection is 75.7 watt. Now for radiation part, I will be using the Stephen Boltzmann law, which is rho A, and it's a dark surface, which means that emissivity is 1. TS4, which is 5.67 10 to the power 8 pi d square by 4 multiplied by my surface temperature in Kelvin 4. So my heat transfer due to radiation on solving this will be 133 watt. So my total heat transfer is due to convection plus radiation, which is 75.7 plus 133, which is 208.7 watt. Now the question says that if the energy associated with energy efficiency associated with energy transfer from heaters to burners is 90%, what is the electric power requirement? So my efficiency is my heat transfer divided by power, which means the total power requirement is my total heat transfer by efficiency. And my efficiency is 0.9. That means the rated power for the electric heater is around 232 watt, which means it should emit the heat of 232 watts, but it is emitting 208.7 watt, which makes the efficiency 0.90%. And at what wavelength is the spectral emission is the maximum? And to find the wavelength, we will use the Vane displacement law to find the maximum wavelength. Vane's law, which gives my maximum wavelength is 2898 in micrometer Kelvin divided by my surface temperature in Kelvin. So on solving this, my maximum wavelength will be 5.54 micrometer. So here in this question, we have given a problem where it says that my surface temperature and my ambient temperature is given, and there is a heat transfer due to convection and radiation. And we asked to find the total heat transfer and the maximum wavelength. So maximum wavelength due to the radiation which emit during the radiation heat transfer. So for finding the total heat transfer, we separately find the convection heat transfer as well as the radiation heat transfer. Since there is no flow, incoming flow from any direction, which means that there is no forced heat convection, there will be a free heat convection going on. And for this, we calculated the Rayleigh number. If there would be a forced convection, we first determine the nature of flow based on the Reynolds number. In the free convection, we determine the nature of flow based on the Rayleigh number. And if the Rayleigh number is less than 10 to the power 9, that means the flow is laminar near the surface. And at far from the surface, there is no flow at all because it's a free convection. So based on the nature of the flow, which is laminar, we use this Nusselt number correlation, and from there we calculated the heat transfer coefficient for the free convection process, and then from Newton's law we found the total heat transfer due to convection. For radiation heat transfer, we use the Stephen-Boltzmann law, and we directly just put the surface temperature into the expression to find the total heat transfer due to radiation. So here the emissivity is 1, which is given in the question, and my total heat transfer is just a summation of 2 heat transfer, which is total combined effect of convection heat transfer and the radiation heat transfer. Then to determine the maximum wavelength, which is emitted due to the radiation heat transfer, we use the Vane's law, where we just need to put the temperature, surface temperature in Kelvin to just directly get the maximum wavelength that it can emit during the radiation heat transfer. So any doubt in this problem?
No, sir.
So okay then. So that's it for today's class. So in the next class, I will come back to this question where I will be more specific. I will be either solving problem which is directional dependent or the wavelength dependent, so we can be more clear about how we should use the concept where the emissive power is directional or the wavelength dependent. So I will be solving problem related to this question or this question itself. Then I will be dig into much deeper into the radiation heat transfer. I may be solving some problems related to the shape factor and all. So yeah, that's it for today.
Okay, sir. Thank you.